Have you ever really thought about where our weather comes from? Every single cloud, every breeze, every heat wave, it all kicks off from one single source, 93 million miles away. Yeah, so let's dive into this because literally every bit of our planet's climate is powered by this incredible journey of energy, all the way from the sun to us here on Earth.
Okay, so imagine for a second that you're a single ray of sunlight. Your journey begins in the fiery heart of the sun, and about 8 minutes later, it ends right here on Earth. We're going to follow that exact trip because if you can understand that one journey, you've got the key to unlocking our entire climate system.
So, how does all this energy actually travel? Well, it arrives as something called electromagnetic radiation. Now, I know that sounds super complex, but really, for the most part, we're just talking about plain old visible light. And the amount of energy we're dealing with, it's just staggering. Get this, more solar energy hits the Earth in a single hour than all of humanity uses in an entire year. Now, when that light finally gets here, it doesn't just stop. It plugs into this really complex system that has, of all things, an energy budget. Yep, just like a financial budget. Some of that energy gets rejected immediately, some of it gets spent right away, and some gets tucked away and saved for later. And here is the breakdown of that budget. A full 30% of the sunlight that comes our way doesn't even really make it into the system. It's immediately bounced right back out into space. The atmosphere itself kind of snags about 20%. And the other half, a full 50%, that gets absorbed by the land and the oceans, right at the surface. And this is a perfect illustration of why some of that energy gets bounced away. You see, the Earth's surface isn't all the same. Bright, light-colored things like clouds, snow, and ice, they act like giant mirrors, just reflecting that energy straight back out. But the dark surfaces, like the deep blue ocean or thick forests, they just soak it all up like a sponge. So, this brings us to a really crucial point, this process of absorption. This is the exact moment that the sun's energy officially enters Earth's systems. When that light gets absorbed, its energy turns into heat, warming up the land, the air, and the water. This is the absolute first step in making weather happen. Okay, so once it's absorbed, that energy gets stored in two huge reservoirs, the atmosphere and the oceans. But here's the wild part. They work in completely opposite ways. The atmosphere, it traps heat with greenhouse gases, which creates a warming effect. The ocean, on the other hand, is so unbelievably vast, it can pull heat from the surface way down into the deep, which actually cools the planet's surface temperature. But here's the thing about energy. It never stays put for long. The planet is in this constant state of trying to find balance. So all this stored heat starts moving around, from the warmer spots to the cooler spots. And it's this constant redistribution that really brings our climate to life. Now, there are a few ways heat gets around. The first, and the simplest, is called conduction. It's just the transfer of heat when two things are literally touching each other. It's exactly like a hot pan transferring heat directly to the food you're cooking. It's a fundamental process for sure, but when we're talking about moving massive amounts of heat across an entire planet, well, conduction is a pretty minor player in the grand scheme of things. The real engine of our climate is this: convection. It's a simple idea, but it is incredibly powerful. When you heat up a fluid, and that can be air or water, it expands, it gets less dense, and it starts to rise. Then, the cooler, denser fluid sinks down to take its place. This creates a constant churning circulation that is fantastic at transferring heat. I bet you've actually felt this yourself. If you spend a day at the beach, you'll notice the land heats up way faster than the water, so that warm air over the land rises, and the cooler, denser air from over the sea swoops in to replace it. That refreshing sea breeze you feel, that's a perfect little convection engine in action. Okay, so now let's take that simple sea breeze and zoom out. Way out, and see how this basic principle builds up into a planetary force that literally shapes our entire world. That exact same idea, warm air rising at the hot equator and cooler air sinking down near the poles, is what drives our gigantic planetary wind systems. The trade winds, the westerlies. They're all just massive convection cells, constantly circulating heat all throughout our atmosphere. And it's not just the air. Convection in the ocean creates something scientists call the global conveyor belt. And it's just this colossal system of currents where warm surface water travels towards the poles, gets cold, sinks to the bottom, and then flows all the way back to the equator. It's basically the planet's heating and air conditioning system, all rolled into one. And these currents, they have huge, real-world impacts. Take the Gulf Stream. It's part of that conveyor belt, and it carries all this tropical heat across the Atlantic. It moves so much energy that it gives Western Europe a much milder climate than it should have, making London's winters feel more like Vancouver's instead of the harsh, bitter cold of Moscow, which is at a similar latitude. So, when you put it all together, from that initial reflection and absorption of sunlight, all the way to the massive engine of convection moving heat through the air and the oceans, you get this. A planet of incredibly diverse climates, from steamy tropics to frozen poles, all of it powered by that one ray of sunlight and its amazing journey. Reflection, absorption, redistribution, all these processes work together to create a climate system that's in this incredibly delicate dynamic balance. Which, of course, leaves us with a pretty critical question. If we start changing the inputs, like how much energy gets reflected or how much gets trapped in the atmosphere, what happens when we start to tip those scales?